Right now, our solar system is drifting through the interior of a vast cavity carved into the galaxy by ancient explosions. This structure stretches hundreds of light years in every direction. It surrounds every planet, every spacecraft, every signal humanity has ever sent into the cosmos. You cannot see it, you cannot feel it. Yet astronomers have confirmed it exists. They call it the local bubble. It is not a theory. It is a real, mapped feature of our galactic neighborhood, a region of superheated, ultra-low density gas left behind by a chain of stellar detonations that began millions of years before our species existed. We are inside it right now, and most people have never heard of it. If you enjoy journeys that reveal hidden structures in our universe, consider hitting that like button and subscribing. It really helps this channel keep exploring the cosmos. Now, get comfortable and settle in. Are you ready? Let's begin. You think you know what surrounds you in space. You have seen the pictures. The sun floats in a scattered field of stars. Beyond those stars, the Milky Way stretches outward for tens of thousands of light years in every direction. Interstellar space is a thin haze of gas and dust, more or less the same everywhere you look, a calm, quiet medium sitting between the stars. That image is wrong, not slightly wrong. Not wrong in some minor technical sense that only matters to specialists. Fundamentally wrong. The space surrounding our solar system, the region you might call our cosmic backyard, is one of the strangest and most unusual environments in the entire galactic disk. And for the whole of human history, we had no idea. We lived inside it. We built civilizations inside it. We launched telescopes and satellites and interplanetary probes inside it. We studied the cosmos from within it, and we never once realized that the sun and everything orbiting it exists inside a vast invisible structure, a cavity carved into the galaxy itself. This structure has no visible walls. It emits no light your eyes could detect. It does not announce itself through any sensation accessible to human biology, and yet it is there. Astronomers have mapped it. Instruments have measured its temperature, its density, its approximate boundaries. Spacecraft data has confirmed its existence through multiple independent lines of evidence. It stretches for hundreds of light years in every direction around us. It has a name. They call it the local bubble. But the name makes it sound small. It makes it sound quaint, like a local pond or a neighborhood park. It is none of those things. The local bubble is one of the largest coherent structures in our immediate galactic neighborhood, and the story of how we found it begins not with a grand theoretical prediction, not with a flash of genius, but with something far more unsettling, a faint glow coming from everywhere at once that nobody could explain. To understand what astronomers stumbled into, you first need to understand what they expected to find. By the middle of the 20th century, scientists had assembled a reasonable picture of the interstellar medium, the thin gas and dust filling the space between stars throughout the galaxy. This material is not distributed evenly. It clumps into clouds of various temperatures and densities, coexisting in a complex, dynamic mixture. Some regions are cold and dense, hovering at just a few tens of Kelvin, packed with molecules like hydrogen, carbon monoxide, and water, shielded from the harsh ultraviolet radiation of hot stars by their own dust. These cold molecular clouds are the birthplaces of new stars. Other regions are warm and diffuse, heated to roughly 6,000 to 10,000 Kelvin by the ambient ultraviolet radiation field pervading the galaxy. This warm gas fills much of the interstellar volume between the cold clouds and represents what most of the galaxy's disk would feel like if you could somehow fly through it at any arbitrary location. It is thin by any terrestrial standard, but it is present everywhere, detectable, measurable, and predictable. It is what astronomers expected to find near the sun. Still, other regions are extremely hot, superheated to temperatures of millions of Kelvin by shockwaves from stellar explosions, but at extraordinarily low densities, so thin that despite their ferocious temperatures, They would feel like nothing at all if you could somehow stand inside them. Together, these phases of interstellar gas coexist in a rough pressure equilibrium across the galactic disk. Cold clouds sit embedded within warmer surroundings. Hot cavities expand and cool over millions of years. The interstellar medium is dynamic, turbulent, and far more structured than the empty void that most people imagine when they think of the space between stars. But there was a general assumption baked into mid-20th century astrophysics. When you zoom out to scales of a few hundred light years, the interstellar medium should be broadly representative everywhere in the disk. The gas near the Sun should not be dramatically different from the gas near any other ordinary star at a similar galactic radius. This seemed perfectly reasonable. The Sun is not located in a special place. It orbits roughly 26,000 light-years from the galactic center, embedded within the Orion arm, which is not even a major spiral arm, just a relatively minor spur between two larger arms. There was no theoretical reason to think our local interstellar environment was anything other than perfectly ordinary. That assumption held for decades, and then it collapsed. The trouble started with X-rays. Earth's atmosphere is opaque to X-ray radiation, which meant that for most of astronomical history, the X-ray universe was completely invisible. Ground-based telescopes could not detect it. Photographic plates could not capture it. The X-ray sky simply did not exist as an observable phenomenon until scientists found ways to get their instruments above the atmosphere. In the late 1950s and 1960s, researchers began launching detectors on sounding rockets, brief suborbital flights that arced above the absorbing atmospheric layers for a few precious minutes of unobstructed observation before falling back to Earth. These early missions were designed primarily to study known or suspected X-ray sources, objects like accreting neutron stars in binary systems, the expanding remnants of stellar explosions, and the intensely hot gas swirling around in massive galaxy clusters millions of light-years away. The science was targeted and specific. Nobody was looking for what they actually found. What they found instead was something nobody had predicted. In addition to the expected bright point sources, the instruments detected a diffuse, soft X-ray glow arriving from all directions across the sky. This was not concentrated in one region of the sky. It was not associated with any single known astronomical object or class of objects. It was everywhere. A persistent, low-level hum of soft X-ray photons arriving from every direction the detectors could point. At first, many researchers treated this as a nuisance. It was background noise, something to be subtracted so that the real sources of interest could be studied more cleanly. But as more rocket flights confirmed the signal, and as the first dedicated X-ray satellites began operating in the early 1970s, the diffuse soft X-ray background proved stubbornly real. It was not instrumental noise. It was not an artifact of the short observing windows or the particular detectors being used. It was not the combined glow of millions of faint unresolved point sources scattered across the sky. The spatial distribution was far too smooth for that explanation. Something was producing soft X-rays uniformly in every direction, and whatever it was, it had to be local. It had to be close. It surrounded the solar system on all sides. The energy of these X-ray photons contained critical information about their source. Soft X-rays, meaning X-rays at the lower end of the energy spectrum, are characteristically produced by gas heated to approximately 1 million Kelvin. Gas at this temperature is fully ionized. Every atom has been stripped completely of its electrons by the intense thermal energy, creating a plasma of bare atomic nuclei and free electrons. This plasma radiates energy in the soft X-ray band as the free electrons interact with the ions, producing photons through a process physicists call thermal Bremsstrahlung radiation. For the diffuse, soft X-ray background to appear this uniform across the entire sky, a large volume of gas at roughly 1 million Kelvin had to surround the solar system in essentially all directions. There was no plausible way around this conclusion. The Sun was embedded inside a region of superheated plasma. This was deeply unexpected. The average warm interstellar medium in the galactic disk sits at roughly 6,000 to 10,000 Kelvin. The cold molecular clouds hover at just a few tens of Kelvin. A million-degree plasma surrounding the Sun implied that our local environment was radically different from what standard models of the interstellar medium predicted for an ordinary location in the galactic disk. The Sun did not appear to be sitting in a typical stretch of galactic space. It appeared to be sitting inside something profoundly unusual, something extraordinarily hot, something that extended far outward in every direction for a considerable and unknown distance. But the soft X-ray background was only the first clue. A second line of evidence, arriving from an entirely different observational technique during the same era, deepened the mystery considerably and pointed toward the same unsettling conclusion. Throughout the 1970s and into the 1980s, astronomers studying nearby stars using ultraviolet and optical spectroscopy began noticing something peculiar about the interstellar gas between us and those stars. When light from a distant star passes through interstellar gas on its way to Earth, atoms in that gas absorb specific wavelengths of light, imprinting dark absorption lines onto the star's spectrum. Different chemical elements produce different absorption signatures at precisely known wavelengths. Neutral hydrogen, the most abundant component of the cooler phases of the interstellar medium, leaves a strong and unmistakable imprint. Sodium, though far less abundant, is another excellent tracer of cold, dense interstellar gas because its optical absorption lines are exceptionally strong and relatively easy to measure from ground-based observatories. What astronomers found was that stars within a few hundred light-years of the Sun showed remarkably little absorption from cold, neutral hydrogen and sodium along the line of sight. This was deeply unusual. In the general galactic disk, cold neutral gas is common. It fills a significant fraction of the interstellar volume at any given location. You cannot typically look more than about 100 light-years in any arbitrary direction within the galactic plane without encountering a measurable column of it. Yet around the Sun, sightlines extending 200, 300, even 400 light-years in certain directions showed almost no sign of cold neutral material whatsoever. The cold gas was simply missing. It had been cleared away, heated, displaced, or destroyed throughout an enormous volume of space surrounding our star. Whatever process was responsible had operated efficiently and thoroughly. Something had swept the local region clean, and the scale of that cleaning was far too large to attribute to any localized phenomenon like a single stellar wind or a single isolated explosion. Think of it like using a tracer dye in water to reveal invisible currents. If you inject colored dye into a flowing river, the color spreads and reveals where the current moves, where it pools, and where it is absent. Sodium absorption functions like a tracer dye for cold interstellar gas. Where you detect strong sodium absorption at short distances from the Sun, cold gas is present nearby along that sightline. Where sodium absorption remains weak or entirely absent even out to distances of hundreds of light-years, something has removed or transformed the cold gas from that entire stretch of space. Astronomers were effectively deploying this tracer dye across the surrounding interstellar medium and discovering a vast region where the dye barely registered at all. The cold gas was not there, and the volume from which it was absent was enormous, extending across hundreds of light-years in multiple directions. Taken together, these two completely independent lines of evidence converged on a single, extraordinary conclusion. The Sun does not reside in a typical stretch of interstellar space. It sits inside a cavity, a vast, roughly enclosed region where cold, dense gas has been evacuated and replaced by extremely hot, extremely thin plasma. This cavity extends for hundreds of light-years in multiple directions, outward from our location. Its interior is mostly barren by interstellar standards, filled only with gas at densities far below the galactic average, and its boundary is defined by the surrounding denser, cooler interstellar medium, the normal gas that should be present throughout the galactic disk, but which is conspicuously absent in our local neighborhood. By the late 1970s and early 1980s, This picture had solidified enough to earn a name. Researchers began referring to the structure as the local bubble, sometimes the local hot bubble. The naming was almost casual, the kind of convenient shorthand that scientists use in conference talks and working papers before they fully appreciate the magnitude of what they have found. But the name stuck. And over the following decades, as observational techniques improved and new data accumulated from ground-based surveys, orbiting X-ray observatories, and ultraviolet satellites, the local bubble grew from a curiosity into one of the most important features shaping our understanding of the nearby galaxy. The first serious attempts to map the three-dimensional shape of the local bubble relied on the same absorption line technique that had revealed the cavity in the first place. Astronomers systematically measured sodium absorption and neutral hydrogen absorption toward hundreds of carefully selected stars at known distances, scattered in all directions from the Sun. Each measurement functioned as a probe, a single narrow sightline piercing through the interstellar medium that revealed whether cold gas was present or absent along that particular path, and at what distance it first appeared. A strong absorption signal appearing at a short distance from the Sun indicated that the sightline had hit the bubble's wall relatively close to our position. A weak or absent signal persisting out to great distances indicated that the sightline was still passing through the bubble's low-density interior without encountering the denser boundary material. Star by star, sightline by sightline, painstakingly accumulated over years of observation, researchers assembled a rough but increasingly detailed three-dimensional picture of the cavity's shape and extent. The result was striking and immediately ruled out the simplest possible geometry. The local bubble was not a neat sphere. It was not even close to spherical. It was irregular, elongated significantly in some directions, compressed markedly in others, and marked by extensions, indentations, and asymmetries that reflected the complex and highly variable density structure of the surrounding interstellar medium through which the cavity had expanded. In the galactic plane, where the interstellar medium is denser and therefore harder to displace, the bubble appeared narrower, its walls closer to the Sun. Toward the galactic poles, perpendicular to the plane of the disk where the ambient gas thins out naturally, the bubble extended much farther outward, possibly opening entirely into the more tenuous gas of the galactic halo above and below the midplane. Some researchers proposed that the bubble might even break through the disk entirely at the poles, a possibility that later observations would explore in greater detail. The overall dimensions were immense by any standard relevant to human experience or human technology. Its walls in the galactic plane lie roughly 150 to 250 light-years from the Sun in most directions, before the surrounding denser medium was finally encountered. Some extensions, particularly toward higher galactic latitudes and in certain specific directions along the plane, reached even farther. The total volume of the cavity encompassed hundreds of thousands of cubic light-years of space. To begin to appreciate what this means, remember that the entire solar system, measured from the Sun out to the most distant objects in the Oort cloud, spans roughly 3 light-years across. The local bubble is larger than the solar system by a factor of many tens of thousands in linear extent and by a staggeringly larger factor in volume. Every planet, every moon, every asteroid, every comet, every spacecraft, every radio signal humanity has ever transmitted into the cosmos exists within a tiny, negligible point suspended deep in the interior of this vast and invisible structure. The early maps were admittedly rough. They suffered from the limited number of suitable background stars available for absorption measurements in certain directions, from uncertainties in the distances to those stars which were often estimated rather than precisely known, and from the inherent difficulty of separating absorption caused by local gas from absorption produced by more distant interstellar material along the same crowded line of sight through the galactic disk. But despite these limitations, the basic picture was robust. It was confirmed independently by multiple research groups using different star samples and different observational techniques. The solar system sits inside a cavity in the interstellar medium. That cavity is filled with hot, thin plasma. Its walls are defined by denser, cooler, surrounding material, and the structure is far larger than anything astronomers had expected to find in the immediate neighborhood of an ordinary, unremarkable star like the Sun. What made this discovery particularly unsettling was not merely the size of the cavity, though that was startling enough to anyone who stopped to think about it. What truly disturbed researchers was the implication for every observation humanity had ever made of the local interstellar medium, every measurement of interstellar gas density in the solar neighborhood, every survey of nearby interstellar dust distributions, every study of the local interstellar radiation field, every estimate of the cosmic ray flux in our vicinity. All of these observations had been conducted from within the local bubble. The data themselves were not wrong. The instruments had functioned correctly. The analyses were sound. The numbers were accurate within their stated uncertainties, but the data were not representative of typical conditions in the galactic disk. We had been studying the interstellar medium from inside an unusual, hollowed-out region and unconsciously assuming that our local measurements reflected average galactic conditions. They did not. They reflected the very specific and unusual conditions prevailing inside a vast hot cavity. And the difference was not trivial. Consider a single example. If you measure the density of interstellar gas by studying absorption lines towards stars within a few hundred light-years, and you happen to be sitting inside a cavity where most of the cold gas has been cleared away, your measurement will come back dramatically lower than the true galactic average. You will conclude that the interstellar medium near the galactic midplane is thinner than it actually is. You will build that conclusion into your models. And every subsequent calculation built on those models, from estimates of how quickly interstellar gas cools and condenses to predictions of where the next generation of stars will form, will carry the error forward. This is exactly what happened. For decades, local measurements of interstellar gas density, dust distribution, and background radiation levels were folded into broader galactic models without any correction for the bubble's influence. The bias was invisible because the bubble was invisible. This realization had immediate practical consequences for interstellar medium research across the field. Models of the galactic gas distribution had been calibrated in part using local observations, and if those local observations were biased by the bubble, then the models needed revision. Estimates of the average density of the interstellar medium near the galactic midplane, the intensity of the local interstellar radiation field, and the baseline flux of galactic cosmic rays in the solar neighborhood all required careful reassessment in light of the bubble's existence. The local bubble was not merely a curiosity for a small community of specialists in interstellar medium physics. It was a systematic observational bias, with implications reaching into multiple branches of astrophysics. And yet, for all the significance of identifying and mapping the cavity, the early observations left the deepest and most important question entirely unanswered. What created the local bubble? What process in nature could evacuate cold gas from a region hundreds of light-years across, heat the remaining material to temperatures of 1,000,000 Kelvin, and maintain that extreme state over what appeared to be millions of years? Nature does not produce cavities on this scale casually. The energy required is immense, far exceeding what any ordinary astrophysical process in the local neighborhood could supply. Something enormously powerful happened in the space we now occupy. Something violent enough to fundamentally reshape the structure of the interstellar medium across a volume of space that dwarfs our solar system the way an ocean dwarfs a single drop of water. Something that occurred millions of years before the first human being ever looked up at the stars, but whose aftermath still surrounds us today, invisible, immense, and inescapable. Several hypotheses were proposed during the 1980s and 1990s. Stellar winds from massive stars could contribute, but the energy budget fell short. The winds were not powerful enough, sustained enough, or concentrated enough to evacuate a cavity of this size. The more compelling explanation involved something far more violent: supernovae. Not one explosion, but a sustained sequence of them. Massive stars detonating one after another over millions of years, each blast expanding the cavity carved by its predecessors. This model was already well established in theoretical astrophysics. Astronomers had observed similar structures elsewhere in the Milky Way and in other galaxies. The physics worked on paper, but confirming it for the local bubble required identifying the specific stars that had exploded, tracing their motions backward through millions of years of galactic time, and calculating whether their combined energy output was sufficient to carve the cavity we observe. Most ambitiously, it required finding tangible physical proof that supernovae had actually detonated in our vicinity within the relevant time frame. And that evidence, when it finally arrived, came from one of the last places anyone in astrophysics had expected to find the fingerprints of ancient stellar explosions, not in the sky, not in the spectra of distant stars, not in the data from orbiting X-ray telescopes or ultraviolet satellites. The evidence was found at the bottom of the ocean, in layers of sediment that had drifted silently through kilometers of dark water and settled onto the seafloor millions of years ago. Pressed into that sediment, mixed in among the ordinary minerals and biological debris of the deep ocean, were atoms that had no earthly business being there. Atoms forged in the thermonuclear furnace of a dying star, launched across light years of interstellar space by the unimaginable force of an explosion, carried on the wind of a shockwave that reshaped the galaxy around us, and deposited gently, invisibly, onto the surface of a planet that did not yet know it was living inside the scar. The discovery of the local bubble had confirmed that the solar system sits inside an enormous cavity in the interstellar medium. Its dimensions had been roughly mapped. Its basic internal properties had been measured, but everything uncovered so far was, in a crucial sense, only the outline of a far deeper and more detailed story. What precisely filled the bubble's interior? How had modern instruments and new space missions refined the early picture? What smaller structures drifted within the vast cavity? And what did the bubble's detailed anatomy reveal about the forces that had shaped it? Answering those questions required an entirely new generation of observations, spanning decades of work, and a willingness to accept that the interior of our invisible cosmic cavity was not featureless emptiness at all. It harboured structure, complexity, and motion that astronomers would spend the better part of a career working to fully understand. Knowing the local bubble existed was the essential first step, but existence and understanding are very different things. By the mid-1980s, astronomers had established that the solar system sits inside a large, hot cavity in the interstellar medium. They had traced its rough boundaries using absorption measurements toward hundreds of nearby stars. They knew it was filled with gas far hotter and far thinner than the surrounding galactic material. They had a name for it, but they did not yet have a detailed picture of what the bubble actually was in precise physical terms. They could not tell you exactly how hot the interior gas was at different locations within the cavity. They could not give you a reliable number for the gas density at the sun's position compared to the density at the bubble's wall. They did not know whether the interior was uniform or structured, featureless or complex. They could not explain with confidence how the bubble maintained itself against the pressure of the surrounding interstellar medium without collapsing inward. And they had only the roughest sense of the bubble's three-dimensional shape, limited by the small number of sightlines available and the imprecise distances to many of the stars used as background probes. Transforming the local bubble from a rough sketch into a detailed physical portrait required decades of additional observation. It required new instruments, new space missions, new techniques for mapping interstellar material in 3 dimensions, and a willingness to revise earlier conclusions when better data demanded it. What emerged from this sustained effort was a picture far richer and more complex than the original discovery had suggested. The local bubble was not a simple void. It was a dynamic structure with measurable physical properties, internal features, embedded smaller structures, defined walls, and connections to the broader architecture of the galaxy. Understanding its anatomy meant understanding the environment in which our solar system has been travelling for millions of years. Start with dimensions. The local bubble is not a sphere. Its shape is highly irregular, sculpted by the uneven density of the interstellar medium through which it expanded and by the locations and timing of the explosions that created it. In the plane of the galactic disk, where the surrounding gas is denser and resists displacement more effectively, the bubble is narrower. Its walls in the galactic plane lie roughly 150 to 250 light-years from the Sun in most directions, though the distance varies considerably depending on the specific direction of measurement. In some directions along the plane, the wall is relatively close, perhaps only 100 light-years away. In others, particularly toward the constellations Canis Major and Puppis, the cavity appears to extend farther before encountering dense material. The irregularity is not random. It reflects the pre-existing structure of the interstellar medium at the time the bubble was inflated. Where the surrounding gas was denser, the expanding shockwave was slowed and the bubble wall formed closer to the explosion site. Where the gas was thinner, the shockwave travelled farther before stalling, producing a more distant wall. Perpendicular to the galactic plane, the picture changes dramatically. The interstellar medium thins out naturally with increasing distance above and below the galactic midplane. The gas disk of the Milky Way has a finite thickness, roughly a few hundred light-years for the cold and warm components, and the density drops off with increasing galactic latitude. The local bubble exploited this vertical density gradient. Its expansion encountered less resistance above and below the plane, allowing it to extend much farther in those directions. Observations suggest that the bubble opens outward toward both galactic poles, reaching distances of 300 light-years or more before its boundaries become difficult to distinguish from the general thinning of the interstellar medium at high galactic latitudes. Some researchers have argued that the bubble does not merely extend upward and downward but actually breaks through the gas layer of the disk entirely, forming an open-ended chimney that connects the midplane to the galactic halo. If this interpretation is correct, hot gas from the bubble's interior may be slowly venting into the halo, contributing to the reservoir of hot, diffuse material observed high above and below the Milky Way's disk. This venting process is one of the mechanisms by which the galaxy regulates its thermal energy balance, cycling hot gas out of the dense star-forming midplane and into the more tenuous halo environment. The total volume of the cavity is enormous. Estimates vary depending on the exact boundaries used, but the local bubble encompasses on the order of several 100,000 cubic light-years of space. To place this in a context that highlights just how vast this is relative to familiar scales, consider that the volume of a sphere with a radius of 1 light-year, which comfortably encloses our entire solar system including the Oort cloud, is approximately 4 cubic light-years. The local bubble contains roughly 100,000 times more volume than this. Everything humanity has ever known, every planet we have visited, every probe we have launched, every signal we have broadcast, occupies a space that could be replicated 100,000 times over within the confines of the structure surrounding us. Now consider what fills this vast interior. The gas inside the local bubble is not absent, there is material present, but it exists at densities so low that by terrestrial or even by ordinary interstellar standards, the interior qualifies as remarkably empty. The average density of the interstellar medium in the galactic plane near the Sun's galactic radius is approximately 1 particle per cubic centimetre. This is already an extraordinarily good vacuum by laboratory standards. The best vacuum chambers on Earth contain billions of particles per cubic centimetre. Interstellar space is incomparably emptier than anything humans can create artificially, but the interior of the local bubble is emptier still. Measurements indicate that the gas density inside the cavity is approximately 100 times lower than the average interstellar value, placing it in the range of roughly 5,000ths to 100th of a particle per cubic centimetre. At these densities, the mean distance between individual atoms stretches to scales that are large even by the standards of interstellar space. The bubble's interior is one of the most rarefied environments in the galactic disk. Almost nothing is there. What little gas does exist inside the cavity is extraordinarily hot. Temperatures in the bubble's interior reach approximately 1 million Kelvin, possibly slightly higher in some regions. At this temperature, every atom of hydrogen and helium is fully ionized. Heavier elements like carbon, nitrogen, and oxygen have been stripped of most or all of their electrons. The gas is a fully ionized plasma, invisible to optical telescopes but detectable through its emission of soft X-ray radiation and extreme ultraviolet light. This is the same emission that originally revealed the bubble's existence during the sounding rocket observations of the 1960s and 70s. The extreme temperature might seem paradoxical given the extremely low density. How can gas be simultaneously almost empty and ferociously hot? The resolution lies in understanding what temperature means at the atomic level. Temperature measures the average kinetic energy of individual particles, how fast they are moving. In the bubble interior, the few particles that exist are moving at tremendous velocities corresponding to 1 million Kelvin. But because there are so few of them per unit volume, the total thermal energy in any given region is actually quite small. If you could somehow stand inside the bubble's hot plasma without a spacesuit, you would not burn. There are simply too few particles striking your skin to transfer significant heat. The individual particles are energetic, but the gas as a whole is so thin that it carries negligible thermal energy in practical terms. However, the story of the bubble's interior emission became more complicated in the early 2000s, when researchers identified a second potential source of soft X-rays that had not been accounted for in the original analysis. Solar wind particles streaming outward from the Sun interact with neutral atoms entering the solar system from the interstellar medium. When a highly charged solar wind ion encounters a neutral atom, it can capture an electron from that atom through a process called charge exchange. The newly captured electron enters an excited energy state and then emits an X-ray photon as it transitions to a lower energy level. This solar wind charge exchange process produces soft X-rays at energies very similar to those attributed to the hot gas in the local bubble. The emission is generated within the heliosphere, relatively close to Earth, and it varies with solar activity. This discovery raised a critical question. How much of the diffuse soft X-ray background originally attributed to million-degree gas filling the local bubble was actually produced locally, within our own solar system, by charge exchange interactions? The answer matters enormously because it determines how much hot gas the bubble actually needs to contain. If a significant fraction of the observed soft X-rays come from charge exchange rather than from distant hot plasma, then the bubble's interior might be less filled with million-degree gas than originally estimated. The relative contributions of the two sources remain an active area of investigation. Current best estimates suggest that both processes contribute meaningfully. The charge exchange emission is real and accounts for a substantial portion of the signal in certain energy bands and certain directions. But residual emission attributable to genuinely hot gas within the bubble persists in the data, even after the charge exchange component is modelled and removed. The local bubble does appear to contain hot plasma, but the amount and distribution of that plasma may be somewhat different from the earliest estimates, which assumed all the observed soft X-rays came from the bubble interior. Within this vast and mostly empty cavity, the Sun is not drifting through a perfectly uniform medium. It is currently passing through a small, partially distinct structure called the local interstellar cloud, sometimes referred to by the more informal name, the local fluff. The local interstellar cloud is a warm, partially ionized cloudlet of gas roughly 30 light-years across, substantially denser than the surrounding hot plasma of the bubble interior, though still remarkably diffuse by any terrestrial standard. Its temperature is approximately 6,000 to 7,000 Kelvin, far cooler than the million-degree plasma filling the wider cavity, but significantly warmer than the cold molecular clouds found outside the bubble in the general interstellar medium. The cloud is composed primarily of hydrogen and helium, with trace amounts of heavier elements, and it is partially ionized, meaning that some fraction of its hydrogen atoms have lost their electrons while others remain neutral. The Sun entered the local interstellar cloud relatively recently, in astronomical terms, likely within the past several tens of thousands of years. It is currently near one edge of the cloud and is expected to exit it within the next 10,000 to 20,000 years, based on the sun's motion relative to the cloud and estimates of the cloud's extent along our trajectory. The velocity of the interstellar gas flowing past the solar system has been measured through multiple techniques, including direct detection by the Interstellar Boundary Explorer satellite and analysis of neutral helium atoms streaming into the inner solar system from the interstellar medium. These measurements indicate a flow speed of approximately 26 kilometers per second relative to the Sun, arriving from the general direction of the constellation Ophiuchus. This means that the interstellar environment immediately surrounding the solar system has not been constant over time and will not remain constant in the future. Before the Sun entered the local interstellar cloud, it may have been immersed in the bare hot plasma of the bubble interior or passing through a different cloudlet entirely. After it exits, it will encounter whatever medium lies ahead along its trajectory, possibly the hot plasma again, possibly another small cloud, possibly a transition zone between the two. The interstellar conditions at the solar system's doorstep are transient, changing on timescales of tens of thousands of years as the Sun moves through the structured interior of the local bubble. The local interstellar cloud is not the only such structure inside the local bubble. Several other small, warm, partially ionized cloudlets have been identified, drifting through the cavity's interior, detected through their subtle absorption signatures in high-resolution ultraviolet and optical spectra of nearby stars. These include the G cloud, which lies adjacent to the local interstellar cloud in the direction of the galactic center, the blue cloud, the apex cloud, and several other smaller features mapped through decades of careful spectroscopic work. These cloudlets are like islands of slightly denser, cooler material scattered across the otherwise barren ocean of hot plasma filling the bubble. They are small relative to the bubble itself, typically a few light years to a few tens of light years in extent, and they appear to move through the bubble interior at velocities of roughly 20 to 30 kilometers per second relative to one another and relative to the Sun. Their total number remains uncertain because the detection of individual cloudlets depends on having suitable background stars positioned behind them at known distances. In directions where few bright nearby stars are available, small cloudlets could easily go undetected. The observed population likely represents only a fraction of the total number of warm clouds drifting through the cavity. Their origin is not entirely settled, and it remains a topic of ongoing research and debate within the interstellar medium community. Some may be remnants of interstellar material that was not fully destroyed or evacuated when the bubble was originally created, dense enough knots of gas that survived the passage of the expanding shockwave and persisted within the cavity as it grew around them. Others may have formed through thermal instabilities in the hot gas itself, condensing out of the million-degree plasma as it cooled in localized regions where conditions favored the formation of a cooler, denser phase. Still others may represent material flowing slowly inward from the bubble walls, detaching from the dense boundary and drifting into the interior under the influence of magnetic fields or pressure gradients. Whatever their origin, these cloudlets represent the small-scale structure embedded within the larger cavity, evidence that the bubble interior is not perfectly smooth or featureless. The properties of the local interstellar cloud directly influence the immediate environment of the solar system in ways that have measurable consequences. The gas flowing past the heliosphere, the protective magnetic bubble generated by the solar wind, comes from the local interstellar cloud. The density, temperature, ionization state, magnetic field strength, and velocity of this inflowing material determine the size and shape of the heliosphere. The interaction between the outward flowing solar wind and the incoming interstellar gas creates a complex, layered boundary region. This region includes the termination shock, where the solar wind abruptly decelerates from supersonic to subsonic speed, the heliosheath, the turbulent zone between the termination shock and the outer boundary, and the heliopause, the outermost surface where solar wind pressure finally balances the pressure of the interstellar medium. Beyond the heliopause, the interstellar gas flows freely, unimpeded by the Sun's influence. The Voyager 1 and Voyager 2 spacecraft crossed these boundaries during their outward journeys from the Sun, directly sampling material from the interstellar medium for the first time in human history. Voyager 1 crossed the heliopause in approximately 2012. Voyager 2 followed in approximately 2018. What these spacecraft measured beyond the heliopause was not the million-degree plasma of the general bubble interior. It was the warm, partially ionized gas of the local interstellar cloud, the specific cloudlet through which our solar system happens to be traveling at this moment in its galactic orbit. The properties Voyager measured, including the local gas density, temperature, magnetic field direction and strength, and plasma characteristics, are broadly consistent with the characteristics of the local interstellar cloud inferred from earlier spectroscopic observations conducted from within the solar system. This agreement between remote sensing and direct in situ measurement provided a powerful confirmation that our understanding of the Sun's immediate interstellar environment is fundamentally correct. Moving outward from the bubble's interior to its edges, the walls of the local bubble represent the compressed boundary, where the cavity meets the denser surrounding interstellar medium. These walls are not sharp, clean surfaces like the shell of a physical container. They are extended transition zones where gas density increases from the extremely low values of the interior to the higher densities characteristic of the undisturbed interstellar medium outside the bubble. In some directions, the transition is relatively steep, occurring over a distance of just a few light years. In other directions, it is considerably more gradual, stretching across tens of light years as the density rises incrementally through multiple intermediate values. The walls contain concentrations of neutral hydrogen, interstellar dust grains, and in some regions, molecular gas, where densities have risen high enough for molecules to form and survive. They are detectable through their absorption signatures in the spectra of background stars, through their thermal emission in infrared wavelengths where dust grains radiate, and through their emission in radio wavelengths, particularly the 21 centimeter spectral line of neutral atomic hydrogen, which serves as one of the primary tools for mapping the distribution of gas throughout the galaxy. Critically, the bubble walls are not static. They represent a dynamic boundary between two very different environments, the hot, thin interior and the cooler, denser exterior. The hot gas inside the bubble exerts thermal pressure outward against the walls. The cooler gas outside exerts its own pressure inward. In a simplified picture, the bubble maintains its structure through this pressure balance. The hot interior pushes out, the cooler exterior pushes in, and the wall sits at the equilibrium point between the two opposing forces. But the real situation is considerably more complex. Magnetic fields thread through both the interior and exterior gas and contribute their own pressure component. Cosmic rays, high-energy particles pervading the interstellar medium, add additional pressure. Turbulent motions in the surrounding gas create dynamic pressure variations that fluctuate over time, and the bubble itself is slowly evolving. The hot interior gas is gradually losing energy through radiation, cooling over millions of years. As it cools, its pressure decreases and the bubble contracts. The walls inch inward, slowly reclaiming territory for the surrounding interstellar medium. Over timescales of tens of millions of years, the cavity will eventually fill in and disappear, its identity as a distinct structure erased by the slow processes of cooling, compression, and mixing. But for now, and for millions of years to come, the pressure balance holds, the bubble persists, and our solar system continues to drift through its interior. The most transformative advance in understanding the local bubble's anatomy arrived in the 21st century with the European Space Agency's Gaia mission. Gaia, launched in 2013, was designed primarily to measure the positions, distances, and motions of stars throughout the Milky Way with unprecedented precision. Over its operational lifetime, Gaia has catalogued more than 1 billion stars, providing distances accurate to fractions of a light-year for objects across much of the galaxy. This extraordinary dataset enabled a revolution in mapping the three-dimensional distribution of interstellar dust and gas. Dust grains in the interstellar medium absorb and scatter starlight, causing distant stars to appear fainter and redder than their intrinsic properties would predict. By comparing each star's observed brightness and color to its expected values based on its spectral type and Gaia-measured distance, Researchers could calculate how much dust lay between the star and Earth along each sightline. Repeating this calculation for millions of stars at known three-dimensional positions produced detailed maps of the dust distribution surrounding the Sun. Because dust traces the cold and warm phases of the interstellar medium, these maps effectively revealed the three-dimensional structure of the gas around us, including the local bubble and its walls. A landmark study published in 2022 by Catherine Zucker and collaborators at the Center for Astrophysics at Harvard and the Smithsonian used Gaia-based dust maps to produce the most detailed three-dimensional reconstruction of the local bubble to date. The study confirmed the bubble's irregular shape, its approximate dimensions of roughly 1,000 light-years from end to end along its longest axis, and the location of its walls in every direction from the Sun. But the study revealed something far more important than geometry. It showed that nearly every prominent young star-forming region within 500 light-years of the Sun, regions associated with the constellations Ophiuchus, Lupus, Chamaeleon, Corona Australis, Musca, and parts of Taurus, sits precisely on the surface of the local bubble. These stellar nurseries, where new stars and planetary systems are being born right now, are not randomly distributed through our galactic neighborhood. They are arranged on the bubble's expanding shell, clustered along the compressed walls, where gas has been swept up and accumulated to densities high enough for gravitational collapse and star formation. This finding transformed the significance of the local bubble. It was not merely an empty hole in the interstellar medium, a void of purely academic interest. It was an active agent of stellar creation. The same explosions that carved the cavity also compressed gas at its periphery. That compressed gas became gravitationally unstable and began forming new stars. The bubble was simultaneously a monument to stellar death and a direct cause of stellar birth. The very stars being born on the bubble's surface today owe their existence to the ancient supernovae that created the cavity millions of years ago. This connection between the bubble's violent origin and the star formation occurring on its rim would prove to be one of the most important insights of modern interstellar medium research. The Zucker study also enabled precise reconstruction of the bubble's expansion history. By measuring the positions and ages of the star-forming regions on the bubble's surface, and by modeling how a cavity driven by sequential energy injections would expand through a realistic interstellar medium, the researchers traced the bubble's growth backward through time. The results indicated that the bubble began forming approximately 14 million years ago, initiated by the first supernovae from a nearby stellar association. Successive explosions over the following millions of years continued to inflate and reshape the cavity. The expansion rate has slowed over time as the driving energy from supernovae diminished, but the bubble has not yet reached pressure equilibrium with its surroundings. It continues to expand today, though at a pace far slower than during its violent early phase. The current expansion velocity of the shell is estimated at approximately 6 to 7 kilometers per second, slow by the standards of supernova blast waves, but sufficient to continue sweeping up interstellar gas and feeding the star-forming regions on its rim. The three-dimensional dust maps also revealed features of the bubble's geometry that earlier studies had only hinted at. In certain directions, the bubble appears to connect to adjacent cavities through low-density corridors or tunnels. These connections suggest that the local bubble is not an isolated structure, but rather one chamber in a larger network of interconnected hot cavities permeating the galactic disk. This interconnected topology is consistent with theoretical models of the interstellar medium, which predict that overlapping superbubbles should create a frothy, porous medium where hot gas can flow between cavities through narrow channels. The local bubble, in this picture, is simply the cavity in which we happen to reside, one bubble in a galactic foam. By the early 2020s, the physical portrait of the local bubble had reached a level of detail that would have been unimaginable to the researchers who first detected the anomalous soft X-ray background half a century earlier. The cavity's shape was mapped in 3 dimensions using millions of stars. Its interior temperature, density, and ionization state had been measured through multiple independent techniques. The small embedded cloudlets through which the sun is currently passing had been characterized spectroscopically and confirmed by direct measurement from the Voyager spacecraft. The walls had been identified as dynamic transition zones containing the raw material for active star formation. The pressure balance maintaining the structure had been modeled with increasing sophistication, incorporating magnetic fields, cosmic rays, and turbulent dynamics. And the expansion history had been reconstructed, linking the bubble's current state to a chain of explosive events stretching back 14 million years. But one element of the story still demanded a full accounting. The anatomy of the bubble was known, its contents were measured, its boundaries were mapped, its expansion was tracked. What remained was the most dramatic piece of all, the precise identification of the explosions that created this structure, the evidence that those explosions left behind, not only in the interstellar medium, but on the surface of the Earth itself, and the extraordinary realization that the bubble's expanding shell had done more than just compress gas. It had triggered the formation of nearly every nearby stellar nursery, meaning that the ancient violence responsible for the local bubble may also be responsible, indirectly, for the next generation of stars and planets forming in our galactic neighborhood right now. The local bubble did not form gently. Nothing about its existence is subtle. A cavity hundreds of light years across, filled with million-degree plasma, surrounded by compressed walls where new stars are igniting right now. Structures like this do not emerge from gradual processes. They do not develop slowly over billions of years through the quiet accumulation of small effects. They are created by violence. Specifically, by the most energetic events the galaxy routinely produces, the deaths of massive stars. A star with more than roughly 8 times the mass of the Sun lives a fundamentally different life than our star does. Where the Sun will burn steadily for approximately 10 billion years, converting hydrogen to helium in its core through a slow and remarkably stable fusion process, a massive star races through its nuclear fuel at a pace that would be reckless if stars could exercise judgment. The relationship between a star's mass and its lifespan is not linear, it is steeply inverse. More massive stars are not merely somewhat shorter-lived, they are dramatically shorter-lived. A star of 15 solar masses exhausts its core hydrogen in roughly 10 million years, a fraction of a percent of the Sun's lifetime. A star of 25 solar masses might last only 7 million years. A star of 40 solar masses burns through its fuel in under 5 million years. These are brief lifetimes by astronomical standards, barely a heartbeat in the context of galactic evolution. The Sun has already existed for 4.5 billion years and is not yet halfway through its main sequence life. A massive star born at the same time as the Sun would have been dead for well over 4 billion years by now, its remnant long cooled, its debris scattered across light years of space. But the brevity of a massive star's life is only part of the story. What matters for the local bubble is how these stars die. When a massive star runs out of hydrogen in its core, it does not simply fade away. It begins fusing heavier elements, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each successive fuel burns faster than the last. Hydrogen fusion lasts millions of years, helium fusion lasts roughly 1 million years, carbon fusion lasts perhaps 1,000 years. Silicon fusion, the final stage, lasts approximately 1 day. When the core fills with iron, fusion stops. Iron cannot release energy through fusion. It is the ash at the end of the nuclear burning chain. Without the outward pressure of fusion energy to support it, the core collapses under its own gravity in a fraction of a second. The inner core compresses to nuclear densities, forming either a neutron star or a black hole. The outer layers of the star, still falling inward, slam into this incompressible core and rebound outward in a shockwave of staggering power. This is a core collapse supernova. The energy released is approximately 10 to the power of 44 joules, liberated in a matter of seconds. To grasp the true scale of this figure, consider that our Sun's total energy output over its entire 10 billion year lifetime amounts to roughly 10 to the power of 44 joules. A single supernova releases a comparable amount of kinetic energy in mere seconds, energy that the Sun requires 10 billion years to produce. The total energy, including neutrinos, exceeds the Sun's lifetime output by a factor of several hundred. Or consider it another way. The total energy consumption of human civilization across all of recorded history, every fire ever lit, every engine ever run, every power plant ever operated, amounts to a quantity so small compared to a single supernova that the comparison is effectively meaningless. The explosion outstrips the cumulative energy output of human civilization by a factor so large it requires scientific notation measured in the dozens of digits. These are not gentle events. They are among the most violent phenomena in the observable universe, exceeded in raw energy output only by gamma-ray bursts and the mergers of compact objects like neutron stars and black holes. The blast wave from this explosion races outward at velocities of 10,000 to 30,000 kilometers per second, slamming into the surrounding interstellar medium with a force that reshapes the local galactic environment across tens of light years. Gas is swept outward, compressed into a dense, expanding shell. The interior is heated to temperatures far exceeding 1,000,000 Kelvin. A hot, low-density cavity forms behind the advancing shockwave, glowing in X-rays and gradually cooling over hundreds of thousands of years as the blast wave decelerates and the interior radiates away its thermal energy. A single supernova can excavate a cavity, perhaps 30 to 50 light-years in radius, under typical interstellar conditions, depending on the density of the surrounding medium and the energy of the particular explosion. Impressive by any human standard, but nowhere near the scale of the local bubble. The bubble extends hundreds of light-years in multiple directions. Its volume is thousands of times greater than a single supernova remnant. One explosion, no matter how powerful, cannot account for what we observe. The energy deficit is too great. The volume is too vast. The arithmetic demands something more. Not one supernova, but many. A sustained bombardment of explosions occurring in sequence over millions of years, each one detonating inside the cavity already created by its predecessors, each one reheating the interior before it could cool, each one driving the expanding shell farther outward into the surrounding interstellar medium. This is the superbubble model. And the question that consumed researchers for decades was straightforward in principle but extraordinarily difficult in practice. Which stars exploded? Where were they when they detonated? And can we identify their parent population today? The answer pointed toward one of the most prominent collections of young massive stars in the solar neighborhood. The Scorpius-Centaurus OB association is a loose grouping of hot, luminous, massive stars spread across a large area of the southern sky, concentrated in the general direction of the constellations Scorpius, Centaurus, Lupus, and Crux. OB associations are not gravitationally bound clusters. They are collections of stars that form together from the same giant molecular cloud complex, but which are gradually dispersing as they orbit through the galaxy. They are identified by their shared motions through space and by their similar ages and chemical compositions. The Scorpius-Centaurus association is the nearest such grouping to the Sun, with its various subgroups located at distances ranging from roughly 300 to 500 light-years from our current position. The association consists of several distinct subgroups of different ages, each representing a separate but related episode of star formation within the larger molecular cloud complex from which the association originated. The three principal subgroups identified through kinematic and photometric studies are Upper Scorpius, the youngest at roughly 10 million years old, Upper Centaurus Lupus at approximately 16 million years old, and Lower Centaurus Crux at approximately 17 million years old. These ages are critical. The oldest subgroups, Upper Centaurus Lupus and Lower Centaurus Crux, contain stars that have been evolving for 16 to 17 million years. The most massive members of these subgroups, the stars born with 15, 20 or 25 times the mass of the Sun, would have exhausted their nuclear fuel and exploded as supernovae within the first few million years of the association's existence. Those explosions began approximately 14 to 15 million years ago, which aligns remarkably well with the estimated age of the local bubble derived from the expansion history reconstructed in the Zuka 2022 study. The timing is not a coincidence. The Scorpius-Centaurus association is the prime suspect because its age, location, and stellar population all match what the local bubble requires. But there is a complication. The Scorpius-Centaurus subgroups are currently located at the bubble's periphery, near its walls, not at its interior. If the supernovae occurred at the present-day positions of these stellar groups, the explosions would have happened at the edge of the cavity rather than at its center. How could explosions at the periphery have carved a cavity that extends hundreds of light years in the opposite direction? The resolution lies in galactic motion. Stars are not stationary. They orbit the galactic center and move relative to one another over millions of years. The Scorpius-Centaurus subgroups have been traveling through the galaxy since their formation. 17 million years ago, the oldest subgroups were located in a different position relative to the Sun and relative to the current bubble boundaries. By tracing the orbits of these stellar groups backward through time, using precise measurements of their current positions and velocities, researchers have shown that the progenitor stars were located much closer to the center of the present-day cavity when the first supernovae began detonating. The explosions happened in the right place. Galactic motion then carried the surviving lower mass members of the association to their current positions at the bubble's edge over the intervening millions of years. Estimates of the number of supernovae required to create the local bubble range from approximately 15 to 20 individual explosions spread over roughly 10 to 15 million years. This figure is derived from the total energy needed to evacuate the observed volume against the pressure of the surrounding interstellar medium, and to heat the interior gas to the observed temperatures. Each supernova contributed roughly 10 to the power of 44 joules, though only a fraction of that energy couples efficiently to the interstellar medium. The rest is carried away by neutrinos and radiation that escapes without doing mechanical work on the gas. Taking this efficiency into account, the total number of required explosions rises somewhat. 15 to 20 supernovae from the Scorpius-Centaurus association is well within the expected yield for a stellar population of its size and age. OB associations typically contain dozens of massive stars that will eventually explode, and the Scorpius-Centaurus association was large enough to supply the required number without difficulty. The sequence matters. The first supernova in the series would have detonated in a relatively undisturbed interstellar medium, creating a modest cavity surrounded by a dense shell. The second supernova, occurring a few 100,000 to a million years later, would have detonated inside this existing cavity, where the gas density was already far lower than the ambient medium. In low-density gas, a supernova blast wave loses energy more slowly and travels farther before decelerating. The second explosion therefore expanded the cavity more efficiently than the first. The third explosion expanded it further still, detonating in an even more rarefied interior. Each successive supernova found itself exploding inside a progressively larger, progressively emptier cavity, allowing its energy to push the shell outward with increasing efficiency. This compounding effect is what allows a sequence of supernovae to create a structure far larger than any single explosion could produce. The cavity grows not linearly with the number of explosions but at an accelerating rate, each detonation leveraging the emptiness left by its predecessors. To illustrate the difference, consider that the first supernova in the sequence, detonating in undisturbed interstellar gas, might carve a cavity 40 light-years in radius. The second supernova, detonating inside that existing cavity where the gas is already thin, might push the shell outward to 60 light-years. By the fifth or sixth explosion, the cavity might span well over 100 light-years. By the 15th, several hundred. The same amount of energy per explosion produces dramatically more expansion when it detonates in a pre-cleared environment. The bubble bootstraps its own growth. Each explosion makes the next one more efficient. The evidence for this supernova origin is not limited to theoretical models and stellar population statistics. Some of the most compelling proof comes from a source that no astrophysicist would have predicted: the floor of the Earth's ocean. In 1999, a team led by physicist Klaus Knie reported the detection of iron-60 in a deep-sea ferromanganese crust sample retrieved from the Pacific Ocean floor. Iron-60 is a radioactive isotope of iron with a half-life of approximately 2.6 million years. This half-life is extremely short by geological standards. Any iron-60 that existed when the Earth formed 4.5 billion years ago has long since decayed to undetectable levels. If iron-60 is present in recent geological deposits, it must have arrived from an external source within the past few million years. And there is essentially only one astrophysical process that produces iron-60 in significant quantities: a core collapse supernova. This makes iron-60 one of the cleanest diagnostic tools in nuclear astrophysics. Unlike stable iron isotopes, which are abundant in Earth's crust and could originate from many sources, iron-60 has no significant terrestrial production pathway. It is not created by volcanic activity, radioactive decay chains, cosmic ray interactions in the atmosphere, or any other known geological or planetary process. If you find fresh iron-60 in a recent geological sample, it came from a supernova. There is no plausible alternative explanation. The isotope is, in effect, a supernova's signature written in atoms. The explosive nucleosynthesis occurring during the detonation fuses lighter nuclei into heavy, neutron-rich isotopes including iron-60. This freshly synthesized material is ejected into the surrounding interstellar medium by the blast wave and disperses over light years of space. If a supernova occurs close enough to a planetary system, some of this debris will be swept up by that system as it orbits through the contaminated region of space. The initial detection by Knie and colleagues was a remarkable achievement in experimental nuclear physics, requiring accelerator mass spectrometry capable of identifying vanishingly small numbers of iron-60 atoms amid the overwhelming background of stable iron isotopes in the geological sample. The detection was confirmed and greatly expanded by subsequent studies over the following 2 decades. In 2016, a comprehensive analysis led by Anton Wallner and an international team of collaborators identified 2 distinct pulses of iron-60 deposition in deep-sea sediment cores retrieved from multiple ocean locations worldwide, spanning the Pacific, Atlantic, and Indian Oceans. The first pulse peaked at approximately 2 to 3 million years ago. The second pulse peaked at approximately 6 to 7 million years ago. The global distribution of the signal, appearing in sediment cores from widely separated ocean basins and in ferromanganese crusts that accumulate material over millions of years, ruled out terrestrial contamination, localized volcanic activity, or any other geological process confined to a single region. The iron-60 came from space. It arrived at Earth embedded in interstellar dust grains carrying freshly synthesized supernova debris, particles that had traveled across light years of space before settling through the atmosphere and drifting to the ocean floor. The timing of these pulses is consistent with supernovae, occurring at distances of roughly 150 to 300 light-years from the solar system, close enough to deliver measurable quantities of freshly synthesized material, but far enough away that the blast waves would not have been directly catastrophic to life on Earth. These distances place the explosions well within the local bubble and are consistent with detonations from the Scorpius-Centaurus Association or closely related stellar groups that shared the same region of the galaxy during that epoch. Additional iron-60 has been detected in lunar regolith samples returned by the Apollo missions in Antarctic snow deposits representing very recent interstellar dust accumulation, and in galactic cosmic ray measurements by the Advanced Composition Explorer satellite orbiting near Earth. Each independent detection confirms the same basic picture. Supernovae have detonated in the solar neighborhood within the past several million years, and the debris from those explosions has physically reached our planet. We are not merely inferring the supernova origin of the local bubble from distant observations of hot gas and absorption line measurements. We have found the ashes of the explosions in our own geological record. The atoms created in dying stars have settled onto the ocean floor, been buried in sediment, and been retrieved by scientists who recognize them for what they are: physical remnants of the violence that shaped the space around us. The Iron-60 detections at 2 to 3 million years ago and 6 to 7 million years ago correspond to only the most recent supernovae in the sequence. Earlier explosions, occurring 10 to 15 million years ago, would have deposited Iron-60 as well, but the isotope's relatively short half-life means that material from those earlier events has largely decayed below detectable levels in geological samples. The earlier supernovae are inferred from the bubble's size, temperature, and expansion history rather than from direct isotopic evidence. The more recent events, however, provide a direct physical link between the local bubble's ongoing history and conditions on Earth. The supernova that deposited Iron-60 2 to 3 million years ago may have been close enough to produce measurable effects on Earth's atmosphere and biosphere, though the magnitude of those effects remains debated. Some researchers have proposed connections between nearby supernova activity and changes in cosmic ray flux, atmospheric ionization, cloud formation, and even biological extinction patterns during the late Pliocene and early Pleistocene epochs. These connections are speculative and not firmly established, but they illustrate the broader point that the local bubble is not merely an abstract astronomical structure. Its history intersects with the history of life on our planet in ways that scientists are only beginning to explore. But the supernovae did not merely destroy. This is where the story circles back to the discovery described earlier, the finding that nearly all nearby stellar nurseries sit on the bubble's surface. From the perspective of the supernova sequence, that finding takes on a deeper significance. Each successive explosion drove the expanding shell farther outward, and as the shell accumulated more swept-up material, it grew denser and more massive. Eventually, portions of that compressed shell crossed a critical threshold. They became heavy enough and dense enough to collapse under their own gravity. The supernovae that killed the most massive stars of the Scorpius-Centaurus association did not merely clear a cavity. They built a wall of compressed gas around it, and that wall became the birthplace of the next generation of stars. The dead gave rise to the living. The explosions that ended stellar lifetimes created the conditions for new ones to begin. Some of the young stars forming on the bubble surface are themselves massive enough that they will eventually explode as supernovae. When they do, their explosions will inject new energy into the bubble's shell or into the surrounding medium, potentially creating secondary cavities that overlap with or extend the local bubble. This process of sequential triggered star formation and supernova feedback is one of the primary mechanisms driving the evolution of the interstellar medium throughout the galactic disk. The local bubble is not a unique or isolated event. It is one instance of a cycle that repeats continuously across the galaxy, with superbubbles inflating, triggering star formation, producing new massive stars, and generating new superbubbles in an ongoing chain of creation and destruction. Now consider where we are within this aftermath. The solar system does not sit at the geometric center of the local bubble. It is offset, located closer to one wall of the cavity than to the other. In the direction of the galactic center and toward the Scorpius-Centaurus association, the bubble wall is relatively close, perhaps 100 to 150 light-years away. In the opposite direction, toward the galactic anticenter and the constellations of Orion and Eridanus, the cavity extends considerably farther before encountering dense material. This asymmetry reflects both the irregular shape of the pre-existing interstellar medium through which the bubble expanded and the off-center location of the original explosions relative to the Sun's current position. The Sun is not stationary within the bubble. It moves through the galactic disk at a velocity of approximately 20 kilometers per second relative to the local standard of rest, carrying the entire solar system along a trajectory determined by the gravitational potential of the Milky Way. This trajectory is slowly carrying the solar system toward the bubble wall in the direction of the constellation Scorpius. though the approach is gradual on any human timescale. At this velocity, the Sun travels roughly 1 light-year every 15,000 years, a pace that seems glacial by human standards but accumulates over astronomical time. Over the past several million years, the solar system has traversed tens to hundreds of light-years through the bubble interior, passing through various regions of the cavity and encountering different local conditions along the way. The path has not been straight. The Sun's orbit around the galactic center is not a simple circle, but a complex trajectory that bobs above and below the galactic midplane with a period of roughly 60 to 70 million years and oscillates radially inward and outward over longer timescales. This three-dimensional orbital motion means the solar system samples different parts of the local bubble over time, crossing through different regions and encountering different densities, temperatures, and cloudlet distributions. The current passage through the local interstellar cloud is one episode in this ongoing transit through a structured environment. Before entering this cloud, the solar system may have been immersed in a different interstellar environment, perhaps the bare hot plasma of the bubble interior or a different warm cloudlet. After exiting, it will continue its journey through the cavity, eventually approaching and potentially crossing the bubble wall into the denser interstellar medium beyond. This transit has real consequences that extend beyond abstract astronomy. The interstellar environment surrounding the solar system determines the external pressure on the heliosphere, the flux of galactic cosmic rays penetrating to the inner planets, and potentially even aspects of Earth's climate and atmospheric chemistry over geological timescales. Changes in the local interstellar density, as the Sun moves from one region of the bubble to another, can compress or expand the heliosphere, modulating the cosmic ray flux at Earth's orbit. Galactic cosmic rays influence atmospheric chemistry by ionizing molecules in the upper atmosphere, which may affect cloud nucleation processes and thereby influence climate. Some researchers have investigated whether passages through denser cloudlets within the bubble might correlate with glacial epochs, shifts in biodiversity patterns, or other climate variations recorded in the geological record. The evidence for such correlations remains inconclusive and is actively debated within the scientific community, but the physical mechanism connecting interstellar conditions to planetary climate is plausible and grounded in well-understood physics. The solar system does not exist in a static, unchanging environment. It moves through a structured medium whose properties vary along the trajectory, and those varying properties have the potential to influence conditions on the worlds within it. The Sun's position within the bubble also means that every astronomical observation we make of the nearby interstellar medium is conducted from a specific, non-central location within the cavity. We see the bubble walls at different distances in different directions. The nearest walls are relatively well characterized because the background stars used to map them are close and bright. The most distant walls, in directions where the cavity extends farthest, are harder to map because fewer suitable background stars are available at those greater distances. This observational asymmetry introduces biases into our three-dimensional models of the bubble that researchers must carefully account for. Our view of the local bubble is shaped not only by the bubble's actual geometry, but by our particular vantage point within it. The combination of all these lines of evidence, stellar population analysis, dynamical traceback of the Scorpius-Centaurus association, supernova energy budget calculations, Iron 60 detections in terrestrial and lunar samples, three-dimensional dust mapping from Gaia, and expansion history modelling converges on a coherent and detailed narrative. Approximately 14 to 15 million years ago, the first massive stars in the oldest subgroups of the Scorpius-Centaurus association reached the ends of their lives and exploded. Their blast waves began clearing gas from the surrounding interstellar medium, creating a small initial cavity. Over the following 10 to 12 million years, approximately 15 to 20 additional supernovae detonated within the growing cavity, each one expanding it further, reheating its interior and driving the shell outward. The compressed shell accumulated enough mass to become gravitationally unstable in multiple locations, triggering the formation of the nearby star-forming regions we observe today on the bubble's surface. the most recent supernovae in the sequence, occurring 2 to 3 million and 6 to 7 million years ago, deposited radioactive iron-60 onto the Earth and Moon, leaving a detectable isotopic signature in geological and lunar samples. The solar system, carried along its galactic orbit, has been drifting through the bubble's interior throughout this entire period, currently passing through the local interstellar cloud, roughly 30 light-years across, slowly approaching the bubble wall in the direction of Scorpius. This is the structure we live inside. Not a metaphor, not a theoretical construct. A physical cavity in the interstellar medium of the Milky Way, carved by the sequential deaths of massive stars, confirmed by observations spanning X-ray astronomy, ultraviolet spectroscopy, radio surveys, spacecraft measurements, three-dimensional dust cartography, and deep-sea geochemistry. The evidence is overwhelming and internally consistent across disciplines that have no reason to agree unless the underlying picture is correct. But the full significance of the local bubble extends beyond the story of its creation and the location of our solar system within it. What does it mean that we live inside this structure? What does the bubble reveal about the broader architecture of the interstellar medium? How does it connect to similar structures throughout the galaxy? And what does it tell us about the relationship between human perception and cosmic reality? But there is one more dimension to this story, and it may be the most unsettling of all. Not that the bubble is dangerous, but that it was invisible. That we spent the entirety of human civilization surrounded by the aftermath of ancient stellar violence without ever suspecting it was there. The universe is full of structures that operate beyond the reach of human intuition, and the local bubble may be the most vivid example we have of how much of our cosmic environment remains hidden in plain sight. The local bubble is not an anomaly. It is not a freak occurrence, a one-time accident that happened to carve out the particular region of the galaxy where the Sun resides. The Milky Way is riddled with structures like it. Across the galactic disk, wherever OB associations have formed and their most massive members have detonated in sequence, superbubbles have been inflated in the interstellar medium. Some are younger and smaller than ours, still being actively driven by ongoing supernova activity within their interiors. Others are older and larger, their energy sources exhausted, their hot interiors slowly cooling toward equilibrium with the surrounding gas. Still others are ancient, long since faded, their cavities filled in and their boundaries dissolved back into the general interstellar medium, leaving no trace except the chemical enrichment their explosions contributed to the galaxy's ongoing evolution. Surveys of the Milky Way and of nearby galaxies have identified dozens of confirmed superbubbles, and the true number is certainly far larger. Many remain undetected because they are located in crowded regions of the galactic disk, where overlapping structures make individual bubbles difficult to isolate, or because they are oriented in directions where observational coverage is incomplete. In the Large Magellanic Cloud, a small satellite galaxy of the Milky Way where the interstellar medium can be viewed face-on without the confusion of looking through the disk edge-on, superbubbles are strikingly visible. They appear as enormous arc-shaped shells and circular voids in maps of ionized hydrogen emission, each one marking a region where stellar explosions have hollowed out the surrounding gas. Some of the largest superbubbles in the Large Magellanic Cloud span more than 1,000 light-years, dwarfing even the local bubble in scale. Within our own galactic neighborhood, the nearest major structure adjacent to the local bubble is known as Loop 1, sometimes called the North Polar Spur based on its striking appearance in radio continuum surveys of the sky, where it manifests as a large arc of radio emission extending from the galactic plane high into the northern galactic hemisphere. Loop I has been studied since the early days of radio astronomy, and was initially interpreted as a nearby supernova remnant. Its true nature has been debated for decades, with some researchers arguing it is a relatively local structure within a few hundred light-years and others proposing it is a much more distant feature associated with activity near the galactic center, thousands of light-years away. Recent evidence, including X-ray absorption measurements and three-dimensional dust mapping, increasingly favors the local interpretation. Loop I appears to be a large shell-like structure associated with the Scorpius-Centaurus OB association, the same stellar grouping responsible for creating the local bubble. This connection is not a coincidence. The Scorpius-Centaurus association has been producing massive stars and supernovae for millions of years across its several subgroups, and the cumulative effect of all those explosions has shaped the interstellar medium across an enormous region of the nearby galaxy. Loop I appears to represent either a separate, younger superbubble inflated by the most recent supernovae from the Upper Scorpius subgroup, which at roughly 10 million years old contains stars that have only recently begun to reach the ends of their massive star lifetimes, or a large expanding shell driven by the combined stellar winds and explosions of the association's current population of hot, luminous stars. Its boundary may partially overlap or abut the local bubble's own wall in the direction of the galactic center. The precise relationship between Loop 1 and the local bubble remains debated. Some models suggest they're entirely separate cavities that happen to lie adjacent to each other. Others propose that they are in the process of merging, with the boundary between them thinning or breaking down as both structures expand. If merger is occurring or has occurred, hot gas could flow freely between the two cavities, creating a larger interconnected region of low-density, high-temperature plasma. This possibility points to a broader feature of the interstellar medium's architecture. Superbubbles do not exist in isolation. They overlap, abut, and merge with one another over time. When two adjacent bubbles expand until their walls meet, the compressed gas between them can be squeezed out, creating a low-density tunnel or corridor connecting the two cavities. Hot gas flows through these tunnels, linking separate bubbles into a larger network. Theoretical models of the interstellar medium have long predicted this topology. The hot phase of the interstellar medium, gas at temperatures of hundreds of thousands to millions of Kelvin, produced primarily by supernova explosions and the powerful winds of massive stars, is expected to fill a significant fraction of the galactic disk's volume, perhaps 20 to 30% or more, depending on the local supernova rate, the density of the ambient medium, and the efficiency with which supernova energy couples to the surrounding gas. This hot gas does not exist as isolated, disconnected pockets scattered randomly through the disk. It forms an interconnected web of cavities and tunnels, a porous, sponge-like or frothy structure threaded through the denser, warm and cold phases of the interstellar gas that occupy the remaining volume. The local bubble, in this picture, is one chamber in a galactic network of interconnected hot cavities. Observations support this interpretation. In several directions, the local bubble's walls appear unusually thin or absent, suggesting that the cavity connects to adjacent low-density regions through narrow channels. One such connection may exist in the direction of the constellation Canis Major, where the bubble appears to extend farther than in other directions along the galactic plane, possibly linking to a neighbouring cavity associated with the Gum Nebula, a large and ancient emission nebula associated with past supernova activity located roughly 1,300 to 1,500 light-years away. Another possible connection exists toward the Beta Canis Majoris tunnel, a low-density corridor identified in absorption line studies that may connect the local bubble to more distant hot regions. These tunnels are difficult to confirm observationally because they are narrow and their low-density interiors produce very faint emission. But their existence is predicted by theory and supported by the patchwork of high and low absorption sightlines that astronomers have accumulated over decades of study. The interconnected bubble topology has implications that extend well beyond local interstellar medium research. It affects how energy, momentum, and chemically enriched material are transported through the galactic disk. Supernovae produce heavy elements, the metals that are essential for forming rocky planets and, ultimately, for the chemistry of life. When a supernova detonates inside a low-density cavity, its ejecta can travel much farther through the rarefied interior than they could through dense ambient gas. If that cavity connects to adjacent bubbles through tunnels, the enriched material can spread across even greater distances, seeding remote regions of the galaxy with freshly synthesized elements. This process may be one of the primary mechanisms by which the galaxy achieves the relatively uniform chemical enrichment observed across large regions of the disk. Superbubbles and their connecting tunnels serve as conduits, distributing the products of stellar nucleosynthesis far beyond the immediate vicinity of each individual explosion. Now return to the word at the center of this episode's title, trapped. We are trapped inside a bubble we cannot see. What does trapped actually mean in this context? It does not mean imprisoned. The local bubble has no walls that prevent passage. There is no physical barrier at the bubble's boundary that would stop a spacecraft or a signal from crossing into the denser interstellar medium beyond. The walls are transition zones, not barricades. In principle, a sufficiently advanced spacecraft could fly from the bubble's interior, through the wall, and into the ambient galactic medium on the other side. The word trapped does not describe a physical confinement. What it describes is something more profound and, in its own way, more confining than any physical wall. The solar system is embedded within a structure so vast that no human technology can traverse it in any practical time frame. The nearest bubble wall, in the direction where it is closest, lies roughly 100 to 150 light-years away. At the speed of the fastest spacecraft humanity has ever launched, the Voyager probes travelling at approximately 17 kilometers per second, reaching the bubble wall would require well over 1 million years. At the speed of light itself, the journey would take at least a century. We cannot visit the boundary. We cannot examine it up close. We cannot step outside the cavity and look back at it from the exterior. We are inside, and for all practical purposes, we will remain inside for the entire foreseeable future of human civilization. More fundamentally, we are trapped by perception. The local bubble is invisible to every human sense. It produces no light that the eye can detect. It emits no sound that the ear can register. It exerts no pressure that the skin can feel. It has no odour, no taste, no texture. A person standing on Earth under a clear night sky, looking upward at the stars and the faintly glowing band of the Milky Way, receives no sensory information whatsoever about the enormous cavity surrounding them in every direction. The stars look the same whether you are inside a superbubble or outside one. The constellations do not change. The brightness of the night sky does not shift. Nothing in the visual appearance of the heavens provides any clue that the observer is located inside a vast region of superheated, ultra-low-density gas stretching hundreds of light-years in every direction. We are embedded in this structure as completely and as invisibly as a fish is embedded in water. And just as a fish born into the ocean has no concept of the ocean as a distinct entity separate from the totality of its experience, humanity had no concept of the local bubble until instruments sensitive to X-rays, ultraviolet absorption, radio emission, and interstellar dust were developed, launched above the atmosphere, and pointed at the sky with sufficient precision to reveal what had always been there. This perceptual confinement is the deeper sense in which we are trapped. For the entire span of human civilization, from the earliest astronomical observations of ancient Mesopotamia and Egypt, through the invention of the telescope and the development of modern astrophysics, we lived inside this structure without knowing it. Every cosmological model, every map of the nearby galaxy, every theory about the interstellar medium was developed by observers sitting inside a vast hot cavity and interpreting their observations without accounting for the bias introduced by their location. The local bubble was there all along. It surrounded every observatory, every telescope, every astronomer who ever lived, and nobody knew. The observational bias introduced by our position inside the local bubble is not a trivial technicality that matters only to specialists in interstellar medium research. It has practical consequences for how we understand the nearby galaxy at multiple levels. The observational bias we have already encountered is itself a symptom of this confinement. We did not merely fail to notice the bubble. We built decades of astrophysical models on data collected from inside it, unknowingly treating an unusual environment as a representative one. That correction is still ongoing. But the deeper lesson is not about any particular measurement error. It is about what the bubble reveals regarding the relationship between observer and cosmos. We do not see the universe from some neutral vantage point. We see it from inside a specific structure, shaped by specific events at a specific moment in its evolution. The local bubble is perhaps the most concrete reminder that every observation is made from somewhere, and that somewhere always leaves its fingerprint on what we observe. The local bubble is not permanent. It is a transient feature of the galactic disk, created by a specific sequence of events and destined to fade over cosmic time. The hot gas filling the cavity is slowly losing energy through radiative cooling. As electrons in the ionized plasma interact with ions and emit X-ray and ultraviolet photons, those photons carry energy away from the gas, and the temperature gradually decreases. The cooling rate depends on the gas density and temperature. At the current conditions inside the local bubble, extremely low density and approximately 1 million Kelvin, the cooling timescale is long, measured in millions of years, but it is not infinite. The process is continuous and irreversible unless new energy is injected. As the temperature drops, the thermal pressure supporting the cavity against the inward push of the surrounding interstellar medium weakens. The pressure balance that has maintained the bubble structure for 14 million years will slowly shift in favor of the exterior. The walls will begin to move inward, gradually at first, then more rapidly as the interior pressure continues to decline. Cool, dense gas from the walls will infiltrate the interior, mixing with the hot plasma and accelerating the cooling process through enhanced radiative losses at the mixing interfaces. Over time, this encroachment will fill the cavity with material that will eventually restore the region to conditions more typical of the general galactic disk. The local bubble will cease to exist as a distinct structure. Its boundaries will dissolve. Its hot interior will cool to temperatures indistinguishable from the surrounding warm interstellar medium. The space we currently inhabit will become ordinary galactic real estate once more, carrying no trace of the cavity that once defined it except in the chemical enrichment contributed by the supernovae that created it. The timescale for this process is measured in tens of millions of years. The bubble has existed for approximately 14 million years already. It may persist for another 10 to 20 million years before its identity as a distinct structure is lost. Over that time, the interior will cool, the walls will encroach, and the cavity will gradually merge back into the ambient interstellar medium. The star-forming regions on the bubble's rim will continue to produce new stars, some of which will be massive enough to explode as supernovae themselves. If those explosions occur near the existing bubble, they could re-inject energy into the cavity, reheating the interior and halting or reversing the cooling process. This would extend the bubble's lifetime and potentially enlarge it further. Alternatively, the new supernovae might create secondary cavities that overlap with the original bubble, producing a more complex, multi-lobed structure. This cycle of creation, cooling, and renewal is one of the fundamental processes governing the evolution of the interstellar medium. Superbubbles are born, expand, trigger star formation on their shells, and eventually fade. The stars born on their shells include new massive stars that will produce new superbubbles when they die. The galaxy breathes through this cycle, inflating hot cavities and letting them collapse over and over across billions of years of galactic history. The local bubble is one breath in this ongoing respiratory process. It is neither the first nor the last. It is simply the one that happens to surround us at this particular moment in cosmic time. The future trajectory of the solar system through the bubble adds another dimension to this evolving picture. As the Sun continues its orbit around the galactic center at approximately 220 kilometers per second, carrying the planets along a path that traces a slow, complex spiral through the disk, it will eventually approach and cross the bubble wall. The exact timing of this crossing is uncertain, depending on the Sun's precise trajectory through the irregularly shaped cavity and on the bubble wall's own slow inward motion as the cavity contracts. Estimates suggest the crossing may occur within the next few million to 10 million years, though precise predictions are difficult given the uncertainties involved. The transition from the bubble's rarefied interior to the denser interstellar medium beyond will change the external environment of the solar system. The heliosphere, currently expanded by the low-density conditions inside the bubble, will be compressed as it encounters denser gas. The flux of galactic cosmic rays reaching the inner solar system will increase as the heliosphere shrinks and provides less shielding. Whether this transition will have measurable effects on Earth's atmosphere or climate is unknown, but it represents a genuine change in the environmental conditions surrounding our planetary system. The solar system has been inside the local bubble for millions of years. It will not remain inside forever. Eventually, we will leave the bubble behind and enter a different interstellar environment, one that our descendants, if they survive long enough and develop the instruments to measure it, will need to characterize from scratch. And now, the question that has been building from the start. What does all of this mean? Not in the technical sense. The technical meaning is clear by now. The local bubble is a cavity in the interstellar medium, approximately 300 light-years across in most directions, filled with hot, low-density plasma, carved by 15 to 20 supernovae from the Scorpius-Centaurus Association over the past 14 million years, with an expanding shell that triggered the formation of nearly all nearby star-forming regions. The solar system drifts through its interior, currently passing through the local interstellar cloud, a small warm cloudlet embedded within the larger cavity. The bubble is confirmed by X-ray observations, absorption line spectroscopy, three-dimensional dust mapping, spacecraft measurements, and the detection of supernova-produced iron-60 in terrestrial ocean sediments and lunar soil. None of this is speculative. It is observed, measured, and cross-validated across independent disciplines. The deeper question is what it means for how we think about our place in the cosmos. And the answer is not dramatic in the way that science fiction might prefer. The local bubble is not a prison. It is not a threat. It is not a conspiracy. It is not a mystery in the sense that it defies explanation. The science is well understood. The physics is clear. The observations are consistent. There is no hidden danger lurking in the bubble's hot interior, no ominous force that threatens Earth or humanity. What is genuinely unsettling is something quieter than that. It is the realization that for the entire history of human civilization, we existed inside the aftermath of ancient stellar violence without any awareness that it was there. Every generation that looked up at the night sky, from the earliest stargazers to the astronomers of the Renaissance to the astrophysicists of the 20th century, was surrounded by a vast, superheated cavity carved by the deaths of massive stars. None of them knew. The structure was too large to see, too diffuse to feel, too far beyond the range of human senses to register in any way. It took the development of X-ray astronomy, ultraviolet spectroscopy, space-based observatories, precision astrometry from missions like Gaia, and deep-sea isotope geochemistry to even confirm that the bubble existed. The most basic fact about our local cosmic environment, that it is not normal, that it is a cavity, that we are inside a scar left by dead stars, required centuries of technological development to uncover. This is not unique to the local bubble. The cosmos is filled with structures that operate beyond the reach of human intuition. Dark matter constitutes roughly 85% of the matter in the universe, yet it is completely invisible to every telescope ever built. Dark energy drives the accelerating expansion of the cosmos, yet its nature remains unknown. The cosmic web, the vast network of filaments and voids that constitutes the large-scale structure of the universe, was invisible until galaxy surveys mapped millions of objects in 3 dimensions. At every scale, from the subatomic to the cosmological, the universe contains structures and processes that human beings cannot perceive directly. We discover them only through instruments, inference, and the patient accumulation of data across generations of scientific effort. The local bubble is perhaps the most intimate example of this hidden architecture. It is not a distant abstraction like dark energy or the cosmic web. It is here. It is the space we occupy. It is the gas through which our solar system moves, the cavity within which every planet in our system orbits, the environment that shapes the heliosphere protecting Earth from galactic cosmic rays. It is as close to home as any cosmological structure can possibly be, and it was invisible to us for the entire span of human history until a few decades ago. The implications of this are worth sitting with. If the most fundamental feature of our immediate cosmic environment went undetected for thousands of years of astronomical observation, what else might surround us that we have not yet found? What other structures might exist at scales too large or too subtle for our current instruments to reveal? The history of astronomy is a history of discovering that the universe is more structured, more complex, and more layered than previous generations imagined. There is no reason to think that process has ended. The local bubble was invisible until it was not. The next hidden structure is waiting to be found. The bubble also forces a reckoning with a subtler idea, that our view of the cosmos is always shaped by the place from which we observe it. We do not see the universe as it is. We see it as it appears from inside a specific structure, at a specific location, at a specific moment in cosmic time. The local bubble colours our observations of the nearby interstellar medium. Our position within the Milky Way colours our observations of galactic structure. Our location in the universe colours our observations of cosmic expansion. At every scale, the observer's position matters. The dream of a perfectly objective view of the cosmos, a view from nowhere, is an aspiration that physics approaches asymptotically but never reaches. Every observation is made from somewhere, and that somewhere has consequences. The local bubble is a reminder of this principle at its most concrete. We spent centuries studying the nearby interstellar medium without realizing we were studying it from inside an unusual environment. The data were real, the instruments worked, the analyses were competent, but the context was missing. Once the context was supplied, once the bubble was identified and characterized, the data took on a different meaning. The observations did not change. Our understanding of what they meant changed profoundly. This is the structure we live inside. A cavity roughly 300 light-years across, filled with million-degree plasma, carved by the deaths of 15 to 20 massive stars over the past 14 million years. Its expanding shell compressed the surrounding gas and triggered the formation of nearly every nearby star-forming region. Its debris has been found in the sediment of our ocean floors and in the soil of the moon. We are drifting through its interior right now, carried along by the sun's orbit around the galactic center, passing through a small warm cloud within the bubble's vast, mostly empty expanse. The bubble will not last forever. In tens of millions of years it will cool, contract and fade, its identity erased by the slow processes of radiative cooling and gas infiltration. New superbubbles will form elsewhere, driven by new OB associations and new supernova sequences. The cycle will continue for as long as the galaxy forms massive stars. The terrifying part of this story, if there is one, is not that the bubble is dangerous. It is not dangerous. The terrifying part is how completely it was hidden, that we lived our entire history inside the remains of ancient stellar explosions without ever knowing, that the most basic feature of our cosmic surroundings was invisible to us until we built instruments sensitive enough to detect what human senses never could. The local bubble is not science fiction. It is not a metaphor. It is a confirmed, mapped, measured astrophysical structure, and the fact that most people have never heard of it is perhaps the most fitting detail of all. The biggest structure in our cosmic neighborhood remains, for most of humanity, exactly what it has always been: invisible, unsuspected, and all around us.